It is history's first man-made building material. It's small enough to hold in your hand, but bind hundreds, thousands, or millions of them together. And these tiny blocks can capture the imagination and help build our future. Yet how this simple material is bonded together can make the difference between triumph and tragedy. From the engineering innovation behind some of our first architectural achievements to an aesthetic for the modern world, born from earth, baptized by fire. Today, new technology is adapting brick to meet the challenges of our civilization. Now, go inside the science of brick. It starts off as a simple block of clay. When put into fire, it turns hard like rock. This transformation has made brick a cornerstone of engineering for more than 9,000 years. Brick is virtually everywhere. No other building material is so central to our history. It gives rise to some of the most famous structures from antiquity, many of which still stand in defiance of time.
It's mind-boggling in one respect because it's hard to realize that something can last that long.
When we pick up a brick and we think of how to use it in a modern building, it is automatically linked to the history of brick architecture and the history of city making.
Today, brick continues to meet crucial engineering needs, from the strength for everyday structures, driveways, chimneys, homes, to the exterior skin of stadiums and skyscrapers. More than 9,000 years after its creation, brick remains an essential material in construction.
I mean, it's an incredible material, brick, and I never cease being fascinated by it. I never cease to being amazed at what is done with it.
Strong, resistant to the elements, virtually fireproof. Brick is prized for its attributes. But brick construction also has a central weakness: mortar. Nowhere is this weakness more evident than in an earthquake. The swaying of the earth can cause mortar joints to fail. The results can be tragic.
Many of the brick buildings built here in the United States are not reinforced or designed to sustain seismic or earthquake loads. They don't like to be shaked around. They don't like to be moved. They don't like vibrations so much. It's not a matter of if, but it is when. If it's a major earthquake, most engineers and architects agree that some buildings will fail in some manner.
Even with this inherent weakness, the demand for this ancient building block continues to grow. Each year, 10 billion bricks are produced in the United States alone. To meet the massive demand, most production is done in state-of-the-art factories. Inside plants like Redlands KF in South Windsor, Connecticut, nearly 50,000 bricks are produced each hour. While technology now drives production, the basic ingredient for creating brick has been the same for centuries: clay. Clay is the soft, wet earth generally found under the first level of topsoil. It is available in virtually every corner of the world. Clay is the same material that gives shape to pottery. But that does not mean all bricks are the same. Select different clays that contain certain minerals, and bricks can be customized for specific traits of color, weight, or strength. The possibilities are vast. Looking for a material that can insulate a furnace? Mine a clay that has iron oxide and silica for maximum resistance to heat. Need a strong material for an industrial factory floor? Select a clay with aluminosilicates for compressive strength. Picking the right clay is a crucial step in brickmaking. Once mined from the earth, clay must be formed. For centuries, humans meticulously created bricks by hand. Today, machines called extruders shape clay. As it's formed, tiny air pockets are pressed out. The result is a block that is less porous. This is crucial.
In that process of actually squeezing that clay out, they actually take the air out of the brick, and that actually takes out the voids and makes the brick stronger and more water resistant.
But to convert clay into brick, it must be fired. Heat is the crucial element that makes it rock hard. Inside these modern kilns, bricks bake at temperatures of at least 1,600 degrees Fahrenheit. At this heat, a transformation takes place. The moisture content inside evaporates. Clay particles start to fuse on the molecular level. This bonding of particles is called vitrification. It turns soft earth into the solid, rock-hard, essential building tool we call brick. Firing bricks requires precision. Bake them too hot or for too long, and the clay literally melts. Not hot enough or not long enough, and you've got a fragile, brittle block. Useless. Modern kilns monitor each variation in temperature. This attention to quality ensures that each brick will be strong, durable, and aesthetically pleasing. Now, go back inside the science of brick. The Great Wall of China. It stretches nearly 4,000 miles. It cuts a path through the heart of a nation. And the strength behind much of this structure, an estimated 3 billion bricks. But this epic barrier almost didn't stand at all. Centuries after it is first built, the wall begins to crumble to the ground. The mud bricks that give it strength are no match for the elements.
The edges of the brick would slowly disintegrate, and then the whole thing would basically turn back into mud and go back into the earth where it came from.
To build a new wall, China needs a stronger brick. They turn to a new material, clay. Less porous than mud, clay bricks are more resistant to penetration by moisture. But sun-dried clay will not be enough. They turn to a crucial element, fire. For at least 3,000 years, the Chinese made pottery by firing it at high temperatures in kilns. They decide to employ the same technology to create brick. By firing the clay in kilns, they can heat it to nearly 2,000 degrees. This allows the molecules to fuse. The result is a hard block that is resistant to the elements and is also able to sustain tremendous weight. The Chinese have a formula to rebuild the wall.
The leap here is looking for something much more permanent. What is strange is how long it takes for this step to be made. And it seems to take a very long time for it to occur to people to fire bricks, building material, rather than just bake them in the sun.
To give the wall greater strength, the Chinese also focus on how to bind the bricks together. The choice of a strong and reliable mortar is essential. In the Great Wall, engineers select a formula of burnt lime and sticky rice gruel. The two components act like cement, sealing the bricks together. Locals dub it the mortar that lasts for as long as 10,000 years. Brick by brick, China restores the largest man-made structure on Earth. The wall as we know it today is finally completed in approximately 1640. More than 300 years later, the wall's clay bricks have stood up to the elements. The very stamps pressed into the clay by brickmakers all across China can still be seen in the finished product. The wall stands as a testament to their skill and ingenuity.
The Great Wall of China is still standing. It's made of brick, and it's still standing.
China employs brick to its full potential for protection. Across the world, another empire transforms it into a backbone of everyday life. Romans employ brick to erect stadiums, temples, and even bathhouses.
Brick has a remarkable quality that it can be used in incremental ways, so it can make an arch. The Romans were really the first to explore this. They were the first to really take it as an intellectual art. How far can we push this simple material? Way past adobe making, but to heroic architecture.
Today, this structure still stands as a testament to the power of ancient Roman brick construction. Trajan's Market. Completed around 110 AD, the market has withstood the passage of time for one simple reason: the Romans' ability to employ brick's strengths and compensate for its weaknesses.
You could say that under Trajan, that brick making in the Roman world was at its apex.
The design for the market calls for a 6-story complex. This means the lower floors will bear incredible weight. In the ancient world, brick is the ideal material to support such mass.
The brick strength is tremendous. You could stack brick 100, 200 feet tall. It will sustain the weight of itself. You could stack 6 or 8 cars on top of a single brick. It will not crush.
The average Roman brick can sustain approximately 5,000 pounds of pressure per square inch. That's the equivalent of a hippopotamus pressing down on every single inch of it at once. Even modern concrete is only required to support 2,000 to 4,000 pounds per square inch. To further increase the brick's ability to sustain the load, the Romans turned to another architectural innovation: the arch.
When we think of the Romans and how they contributed to brick construction, the first thing that comes to mind is the arch. The arch is essentially a very perfect compression element. It's a very clever way to force brick, to force masonry to work in compression only.
To create these arches, bricks are carved into wedges, then painstakingly shaved and sanded by hand to precise measurements in order to fit securely. Nearly 2,000 years later, you can still hardly fit a playing card between the bricks. But the greatest innovation in Trajan's Market is a secret inside the walls. Roman bricks are not the same blocks used by the Chinese. Long and square, they resemble thick tile more than anything else. By cutting these bricks like a pizza into halves, quarters, or even eighths, Romans create a formula for incredibly stable walls. The outside of the wall is straight and flat, but this is just a facade. Behind it is another material that gives it even greater strength: concrete.
They'd use this face brick, arches and stacked brick, and then they would fill the inside of the walls with concrete or grout.
The jagged, sharp edges of the brick triangles bond perfectly with the concrete.
So each little bit of concrete had a place to put his thumb and forefinger, so it gave it a mechanical retention as well as just an adhesive retention. It's just good engineering.
What this did, in essence, is create a composite wall, brick and concrete, and they gained more strength still.
Brick's compressive strength combined with the use of concrete allows Trajan's market to become an ancient high-rise. Now, go back inside the science of brick. London, England. This legendary city turns to brick to overcome one of the greatest disasters in its history. In the process, London redefines how this material will be made and used. September 2nd, 1666. Flames engulf London. Over 3 days, the losses are staggering. 13,000 houses, 87 churches, and countless businesses. The city lies in ashes. As Londoners clean up the wreckage, they notice something amazing. The flames that rage through the city stop right here. This is part of the ancient city wall. It is made of brick, and it is entirely unharmed by the flames. In fact, seemingly every time the fire reaches a brick wall, it stops in its tracks. The reason? Brick is fireproof. When clay is fired in a kiln, the particles inside fuse together into a new molecular structure. The result is a rock-hard substance that will not melt unless it is pushed to more than 2,000 degrees. In essence, brick is virtually immune to typical fires.
It's already been fired in a furnace for days before you ever get to use it. So its properties were actually gained by its thermal sintering of the components together. And so you come along and heat it back up to the kind of temperatures of a kiln, which would not be uncommon in a fire. It sort of says, oh, back in the kiln.
In the wake of the London fire, Christopher Wren, the chief builder to the king, imposes new regulations on all reconstruction. Every new building must be made from fireproof materials. London turns to brick.
People wanted to use fireproof products that could withstand any kind of catastrophe that would come around.
But the city also needs to build quickly. Brick construction is incredibly time-consuming. From the earliest brick structures up to the modern day, each building has gone up the same way. Brick by brick, each one painstakingly laid by hand. Typical square blocks make progress even slower.
There's beauty in the shape of the brick, which comes from a supreme economy. Some of the early bricks would typically be square, but square brick isn't terribly efficient.
London looks to a different shape of brick. Rectangular. Able to fit in a human hand, these rectangular blocks permit masons to raise structures quickly and efficiently. This shape also brings an added benefit: strength. The rectangular shape allows one brick to lay directly across two bricks below it that are facing in another direction. This stacking system gives walls strong patterns that distribute weight over a larger area, increasing both compressive and lateral strength. From churches to hospitals to private homes, brick restores London to a great world capital. England, mid-1840s. Renowned engineer William Cubitt sets out to run a rail line from London north to Edinburgh. In the way is an enormous obstacle, the Mimram Valley. Cubitt looks to an engineering masterpiece for inspiration. He elects to use 40 massive arches modeled directly after the Roman aqueducts to span the distance. The strength of the arches will permit the viaduct to carry great weight with fewer bricks for construction. After just 2 years of construction, the viaduct opens in 1850. It quickly begins to buckle under the train traffic.
As the use of brick developed and major cities wanted to use it for projects like viaducts and bridges, they discovered that brick has its weaknesses. They don't like to be shaked around. They don't like to be moved. They don't like vibrations so much.
In essence, each train is like a mini earthquake, slowly shaking the bricks side to side, causing them to crack. Engineers need a new solution. The answer lies in a completely different kind of brick, engineering or pressed brick. All bricks have tiny pores or air pockets that can act as weak spots when they encounter force. Engineering brick is made by mechanically pressing the clay to be less porous, increasing strength.
Well, engineering bricks came about largely because of the railways, where there was a need for a brick with compressive strength.
In 1930, engineering brick is used to reface the entire viaduct. More than 150 years after it's first erected, Digswell continues to provide safe passage between London and Edinburgh. Now, go back inside the science of brick. It stretches half a city block. It stands nearly 200 feet tall and is composed of almost 600,000 bricks. The Monadnock Building in Chicago is a landmark in American architecture. When it opens in 1892, the Monadnock is hailed as a marvel of engineering. Today, it represents something very special in the history of brick, its downfall. The Monadnock is the last all-brick high-rise in the world. In the mid-1800s, a new invention is revolutionizing the world, the elevator. People can now travel up and down with great ease. Architects start to think in a new way, vertically. Chicago embraces the trend. Recovering from a devastating fire in 1871, much of the city is rebuilt in fireproof brick. Brick's ability to carry heavy loads also makes it a logical choice to erect the high-rise.
You can stack a brick over 1,000 feet high before you'd ever crush it. Brick's compressive strength, and this is how much pressure it will take to actually push the brick down, is somewhere in the range of around 11,000 pounds per square inch, which is very high.
1889. Architects Daniel Burnham and John Wellborn Root planned to build the tallest brick office building on the planet. The Monadnock will stretch 16 stories above the heart of Chicago. To erect a building to such heights, engineers need to conquer a crucial problem: brick's lack of lateral strength. When a brick wall encounters stress from the side, the mortar holding it together can fail. Some engineers at the time believed that any brick building over 10 stories will get knocked over in a strong wind. How will the Monadnock combat the legendary Chicago winds at 16 stories? The answer seems simple. Add thickness to the walls. Walls in an average brick building are usually 1 to 2 feet thick. For the Monadnock, engineers triple that to 6 feet thick on the ground floor. But the apparent solution creates a tremendous problem. The completed Monadnock weighs an estimated 50,000 tons. The building is so heavy, it begins to sink. The Monadnock is designed to showcase brick's potential for high-rise construction. Instead, it highlights the material's limitations. Just 2 years after the Monadnock opens, an addition is made. Another massive building stretching half a city block. The new structure seems identical to the original, but beneath the brick is a secret, a steel frame. In the 19th century, the mass production of steel emerges and changes the face of construction. Lightweight, flexible, and strong under lateral stress, steel is seemingly everything brick isn't. Steel permits the frame of the addition to be much thinner and lighter than the walls of the original. The addition to the monadnock represents a new chapter in brick construction, composite buildings. Steel gives architects a new tool to build higher, stronger, and faster. As buildings soar ever higher, brick takes on a new purpose: aesthetic beauty.
It is really, really, really thick paint that lasts a long time. And because of its traditional look, there's a great many people who prefer the aesthetics of the brick.
The Chrysler building, with its wonderful Art Deco top in New York, is clad in 3 million blue glazed bricks. So brick ceases to be used as a structural material, but it retains great importance as a decorative cladding.
Before, we used brick as the load-bearing element, and there was something covering it, and brick was the sort of utility part of it. Nowadays, though, brick is now the aesthetic part, and behind the brick is some type of steel or concrete frame, which is taking all the load.
Today, just down the street from the monadnock, a new composite building stretches into the sky. At 50 stories, the Columbian will be the tallest brick building in Chicago. Its frame will be fashioned out of nearly 3,000 tons of steel and more than 50 tons of concrete. And on the outside, it will be adorned with over 450,000 bricks.
Back in the turn of the century, when they were building the Monadnock building and other buildings like that, architects and builders were limited to how high they could build the masonry. Today, we've got the Columbian, it's 50 stories high. Same material, brick, on the outside. And while a lot of the construction has changed and a lot of the design aesthetic has changed over the years, brick absolutely has a timeless quality about it.
While using the modern materials of steel and concrete allows engineers to build stronger and faster, modern composite buildings bring new challenges. In composite buildings, moisture can collect between the internal structural walls of concrete and steel and the brick exterior. The result can be erosion and decay at the core of the building. Eliminating that moisture is crucial.
We need a drainage system for these walls, considering that we're in the northern part of Illinois where the weather changes dramatically from winter to rain, and then we have the real hot summers and the fall and the moisture.
In the Columbian, the solution is a 2-inch cavity wall that collects the water and drains it away from the building. The technique bricklayers use to make this happen is an intricate one. Before starting a row of bricks, the mason sets down a steel shelf that is covered with a rubberized waterproofing surface. He places a piece of rope in the mortar between bricks. This will act as the wick to carry the water away from the interior wall. The water will be safely carried outside the building, where it can't do any damage. Composite buildings permit brick to soar higher than ever before. No longer bearing the structural load, it is the beauty of brick that allows it to survive in the world of modern construction. Now, go back inside the science of brick. Strong, durable, virtually fireproof. Bricks have been a cornerstone of engineering for nearly 10,000 years. But when brick construction goes bad, the results can be deadly. As brick construction ages, the mortar that binds the bricks together can wash away. Without regular maintenance, once solid brick walls can become death traps. Nowhere is the need for proper building maintenance more clear than in New York City. It is home to nearly 600,000 brick structures, many of them unreinforced masonry construction. This is New York City's Center for Emergency Response. It is also the headquarters for the city's top authority for building safety, the Building Department's Special Forensic Unit.
You can show the collapse condition inside the building.
You can look at 7.
Today, they are on their way to inspect an aging and abandoned group of apartment buildings in Harlem, which are in danger of collapse. Harlem has some of the most beautiful housing stock in the city, much of it more than 100 years old and carefully restored. But some buildings have missed out on Harlem's recent boom. Today, the forensic team is evaluating the safety conditions of a group of apartment blocks built in the 1890s. They have been abandoned by their owners and now belong to the city's Department of Housing, which must evaluate if the brick structures can be saved or must be torn down.
You notice some bricks are missing. It's very deteriorated by...
When the forensic unit gets a call to go in to have a look at the building, we know that the structural deterioration is advanced. We've lost floors, we've had fires, partial wall collapses. So what we're going in to do is to evaluate to make sure that it's safe.
The structures were built more than 120 years ago using construction techniques that can be traced back to ancient Rome and the rebuilding of London. All windows are supported with Roman brick arches based on those at Trajan's Market. But years of neglect mean that the mortar that once held the bricks together has been largely washed away. To evaluate the state of the buildings, the team must get dangerously close to the loose brick wall.
There's been a lot of fires on the inside. What we have is 40 years of neglect, 40 years of lack of repairs. The wall starts to come apart almost in the same manner that it was put together. So when you're walking around the job site, the bricks can fall down in an unpredictable manner.
Watch your head, watch your head.
To evaluate the building's potential for rehab, the team must inspect its long-hidden foundation.
How is it inside?
It's not too bad. The brick's stable.
I believe I have an inherent sense of when something's going to be, a bad situation for us to go in.
Careful, careful.
You build up a sense for the conditions that you're walking into. They can be dangerous, but that's what we do.
The brick arches are in good condition.
They discover that the huge structure is supported on a base of brick arches.
How is the mortar here? It's okay.
It's stable. It's drying.
Amazingly, the 120-year-old masonry is holding firm. It is the steel-reinforced beams that show the most decay.
No, the steel here is flaking on the...
To do a complete rehab, these aging metal beams must be reinforced or replaced.
Very careful, of course.
Visiting the upper part of the building poses a special risk from ceiling collapse. Any misstep here could be deadly.
Second floor joists are collapsed in this area right above us.
While the wooden interior floors have collapsed, the building's brick walls remain solid.
And the wall seems pretty acceptable from the interior, but...
Crucial mortar shows signs of decay.
The mortar is just, you can remove it with the finger.
To make this building habitable once again, these gaps must be repaired. The team's evaluation today is that the buildings are a hazard, but their brick frames essentially sound. The final decision to restore or rebuild can now be made by city officials.
I believe the buildings can be brought back relatively easily. It's commonly done. We have one right here behind us. We have the original version of the building which has been restored, and right beside it we have a 100-year-old neglected, abandoned 6-story walk-up.
But from the earliest brick construction up to modern buildings, these structures have all faced a lethal enemy. Earthquakes. earthquakes. When the earth starts to buckle, bricks' inability to move from side to side with the quake can bring them tumbling down.
And when the ground shakes and a building tries to follow the ground, some parts of the building go into tension and some go into compression. The parts that go into compression, not a problem. But the parts that go into tension, really bad news for.
Now, go back inside the science of brick. From San Francisco to Los Angeles, to Iran, to the Philippines, the picture repeats itself. In the aftermath of a seismic event, brick buildings are often reduced to piles of rubble. A primary victim of earthquakes are buildings with traditional brick construction. With no steel or other reinforcement, their structural stability can fail with a strong enough force. And even in modern composite buildings, bricks can crumble in an earthquake. While steel and concrete keep the core of the structure intact, the brick facing falls away. The reason for the failure is simple: mortar. Mortar is brick's Achilles heel. When a brick wall encounters a violent lateral force, the mortar holding the bricks together starts to crack. If the force is strong enough, the mortar separates from the brick and the wall comes apart.
Not only will you see piles of brick on the ground after an earthquake in news footage, but you'll see half the bricks look like they could be sold in the garden store tomorrow. I mean, there's not even any mortar sticking to them. They're just bare bricks sitting there.
For decades, engineers have been seeking to solve the weakness of mortar joints. A new technology is currently being employed in Tacoma, Washington. When completed, this 6-story building will provide apartments to faculty and students at the University of Washington. Erected with a central core of steel and concrete, the building will be faced with more than 10,000 bricks. To secure them to the building, engineers are using a new invention, the seismic tie. Made of steel, the ties literally attach the bricks to the interior concrete and steel structure of the building.
The ties we're using are attached like this, and then the 9-gauge wire nestles into it, which allows the building to move different from the masonry. The masonry can shift up and down this much compared to the backup of the building and still be attached to the building.
The ties permit the brick walls to move independently of the primary building during a seismic event, but still remain attached. Thus, the mortar and bricks are able to move in unison, eliminating the tension that causes them to break under force. Securing the brick to the structure of this building is crucial. Tacoma and nearby Seattle sit directly on a fault line. February 28, 2001, 10:54 a.m. The Seattle region experiences a shock registering a magnitude of 6.8. Many of Seattle's landmark brick structures suffer severe damage. Brick mason Jim Reynolds is working on a construction site when the quake hits, but it's one equipped with seismic ties.
The new buildings we were working on had masonry veneer. Because of the seismic attachment, the brick, it just undulated with the wave-like motion of the earthquake.
The seismic tie has great potential for new construction. But what about existing brick structures? There are countless brick buildings in earthquake zones all across the country. But if reinforcement isn't done, many of these buildings are little more than sitting ducks.
If we fool around with structures that we know are seismic liabilities and wait long enough, nature will take care of the problem for us.
In many instances, adding steel or concrete or installing seismic ties is costly or impossible. But a new technology is attempting to solve the problem by reinforcing brick from the outside. It's a space-age fiberglass fabric with 5 times the strength of steel. This fabric can permanently bond to brick with a special epoxy. The fabric is designed to help a brick wall survive the force of an earthquake.
You're combining the positive attributes of a brick wall, which are very good in compression, with the positive attributes of composites, which are very good in tension.
A properly adhered and bound building won't drop its brick on bystanders in a seismic event. You still preserve the brick. The epoxy reinforcement is very strong.
In this test, the sledgehammer simulates the same type of violent force a brick wall encounters in an earthquake. When the sledgehammer strikes the side of the wall that has not been treated with the fabric, it crumbles. Strike after strike, the mortar and bricks fail. Brick by brick, the wall collapses. On the side of the wall treated with the fabric, the results are incredibly different. With each strike, the fabric disperses the force. The bricks and mortar are held securely in place. This fabric has incredible potential. It could provide greater support and safety for countless unreinforced brick buildings around the world. For nearly 10,000 years, brick has given shape to our world. From simple blocks of mud, to composite buildings, to space-age technology, human ingenuity continues to reinvent brick, keeping this ancient creation on the cutting edge of modern construction. But this material's greatest attribute may be our long connection to it.
I think brick has a unique quality. We almost sense in our bones its history. It's a material that we just understand. It makes us feel good. When buildings are made out of brick, we feel good.
It's an incredibly aesthetic and beautiful material. People are comfortable with it. They like to see it. They like to look at their building and feel like it's strong.
It's a process of the earth, and we understand it returns to the earth. So it's one of these materials that just makes sense.
If brick is anything, it is a material that continues to adapt. Today, it is responding to the emerging challenges of our world, and it's helping to lay the foundation for our future.